Chemistry, the Central Science, Chapter 9, Molecular Geometry and Bonding Theories, Lesson 1. So in the last chapter, we looked at how do we draw Lewis structures. So now we're going to look at some bonding theories. And the first one we're going to look at is called VSEPR, or valence shell electron pair repulsion. So this is looking at the fact that we can predict the geometry of the molecule due to the fact that there are repulsions between electrons, right? Both bonding and non-bonding. And we call these types of pairs domains. So for example, in carbon dioxide, we have two double bonds, which means two electron domains. So even though it's a double bond, we don't count it as four individual bonds because double bonds are in the same place that a single bond would be, and the same thing applies for a triple bond. So we effectively have two things surrounding the central atom. In ozone, when we look at our central atom, this is always our central atom that we're concerned with. We have a single bond, a double bond, and a lone pair. So we have two oxygens around the central oxygen, and then we have a lone pair that has to take up space. So we have a total of 3 electron domains. And then if we look at ammonia, we have 3 single bonds and 1 lone pair on the central atom, which then adds up to 4 electron domains. So what we're going to do is look at our Lewis structures once we've drawn those correctly and simply count the number of atoms around the central atom and the number of lone pairs, and that will tell you your electron domain. And from there, then you can determine your molecular geometry. So electron domain geometry is taking into account all of the electrons on the central atom, whether they're bonded or non-bonded, right? Lone pairs, or we have connections to other atoms. That's the total. Your molecular geometry is only concerned with the bonded pairs of electrons because we don't see electrons. We can see the atoms. And what it is that lone pairs of electrons will affect the overall shape of the molecule. And then we can look at bond angles, which is the angle between bonded atoms off of the central atom. So if you have a linear shaped molecule, the bond angle is 180. Trigonal planar, and so a linear is 2 electron domain. Trigonal planar would be 120 degrees, separates the bonds. Tetrahedral, you have a bond angle of 109.5. Trigonal bipyramidal, you have bond angles of 90 and 120. And octahedral, you have bond angles of 90 and then, of course, 180 from the top atom to the bottom atom. So each of these are showing the molecular geometry in terms of how many electron domains do we have. Linear is 2, trigonal planar is 3, tetrahedral is 4, trigonal bipyramidal is 5, and octahedral is 6. So when all of the electron domains are bonds, then those are the shapes that we have. So to determine the shape of the molecule, you draw your Lewis structure, and then you're going to count the number of bonded pairs of electrons or atoms around the central atom and the number of lone pairs on the central atom. And it's always just about the central atom. Then you use the VSEPR model and you're counting, right? You're counting and then you're adding, and then we can determine the molecular geometry by considering only the position of the atoms. So the next 2 slides are going to show molecular geometry with no lone pairs. So beryllium chloride is linear, so no lone pairs on beryllium. It can only form 2 bonds. Boron trifluoride would give you a trigonal planar structure, which is 120 degrees angle. And then methane, which is CH4, is tetrahedral with 109.5 degrees. So in each of these instances, your electron domain geometry and your molecular geometry are the same because everything is bonded. There are no lone pairs. In phosphorus pentachloride, we have trigonal bipyramidal, so 5 atoms surrounding the central atom. We have bond angles of 90 degrees and 120 degrees. And then sulfur hexafluoride is octahedral, right? 6 atoms surrounding a central atom with bond angles of 90 degrees and, of course, 180 from top to bottom. So then what happens to our bond angles when we have lone pairs of electrons on our central atom? So here we're comparing methane, CH4, to ammonia, NH3, to water, H2O. So as we start to increase the number of lone pairs, we start to effectively squish the bonded pairs of electrons together. Why is this? Well, lone pairs don't have to occupy a specific space. If you're bonding, the electrons have to be between those two atoms. So the lone pairs of electrons are existing in their orbitals, and they're able to spread out more, right? So that's what we're showing here with the orange colored lobes. So in methane, it's a tetrahedral geometry and electron domain, so the bond angle is 109.5. The electron domain geometry for ammonia is still 4. It's tetrahedral. However, we've replaced an atom with a pair of electrons, so now our bond angle is smaller, of 107.3. And then with water, we replace, again, another atom with a lone pair of electrons. We still have 2 total atoms plus 2 lone pairs, which is 4. So the electron domain geometry is tetrahedral. However, our shape is bent. So the more lone pairs of electrons we have, the more we see a deviation from our typical bond angle, comparing it to if everything was just a bonded atom. So in this table here, and you have a table in your book that is very similar to this, is showing what molecular geometry do we get once we start introducing lone pairs. So in the top row here for SO2, we have electron pair geometry of trigonal planar, but because we have 1 lone pair of electrons, the shape is bent. The next 3, we can see that they all have tetrahedral as their electron domain, because you either have 3 bonds, 1 lone pair, 2 bonds, 1 lone pair. Oops, sorry, I meant the next 2. And so that results in trigonal pyramidal or bent. Now we have the next 3, where we have a total of 5 pairs of electrons around the central atom. If you have 4 bonds, 1 lone pair, it's called seesaw in shape. If you have 3 bonds, 2 lone pairs, it's called T-shaped. If you have 2 bonds and 3 lone pairs, you end up with a linear molecule. So this is shown in SF4, ClF3, and I3-. And then lastly, we have our electron domain geometry, where we have 6 total pairs, so octahedral. However, if we have 1 lone pair but 5 bonds, we end up with a square pyramidal shape. If we have 4 bonds and 2 lone pairs, we end up with square planar, as shown in BRF5 and XEF4. And we would see deviations from our typical bond angles because now we have these lone pairs of electrons that are squishing the bonds together, right? Electron pair repulsion. Says so in the name, right? Valence shell electron pair repulsion. Why do we get these shapes? Because electrons repel each other. So once we've identified our shape, then we can look at, is the molecule overall polar or nonpolar? In the last chapter, we looked at how to figure out whether we have a polar bond. That's by looking at electronegativity differences. And so when you do electronegativity differences, it's not additive. So each individual bond, it's just one connection. N to H is one, N to H is another, N to H is another. They happen to all be the same. And nitrogen is more electronegative than hydrogen, so it's pulling the electrons towards it. So we see a resultant dipole moment of 1.46 dBs. This is basically using vector math. Beneath this, we see the electrostatic potential map for ammonia. And remember that the blue region is cool, which means there's not a lot of electrons, and the red region is hot, where there are a lot of electrons. So this shows that the electrons are sitting there on top of the nitrogen atom, or they're being pulled that direction. How is that different than nitrogen trifluoride? Well, now fluorine is more electronegative than nitrogen, so it's pulling the electrons towards it. And if we add up those vectors, we see a resultant dipole moment where most of the electrons are concentrated towards the fluorine atoms. The dipole moment is 0.24 dBi. And from the electrostatic potential map, we can see the red regions, which show where there's an electron concentration. Of course, we have that lone pair sitting on top of the nitrogen, which is why it's red up there. but towards all of the fluorine atoms, it's very red as well. So polarity and dipole moments, and it's a tug of war on electrons, and if we have an even pull on each and every side, right, in equal and opposite directions, then dipole moments cancel out, and overall, then you have a nonpolar molecule. So BF3, we see it's trigonal planar, so you can imagine stretching out in a triangle, right at the vertices of a triangle. Fluorine is pulling those electrons towards it in equal and opposite directions. So even though the individual bonds are polar, the molecule itself is nonpolar. In CH2Cl2, we know that chlorine is more electronegative than carbon, so it's pulling electrons towards it. Hydrogen and carbon, the electronegativity difference is only 0.4, so we would consider those to be nonpolar bonds, although carbon is slightly more electronegative than hydrogen. But we can see that we would end up with a polar molecule because we don't have an equal distribution. We do not have an equal pull on our electrons. And by looking at the electrostatic potential map, our slightly negative region would be towards the chlorines, and our slightly positive region would be near the hydrogens. So you can look at adding up dipole moments. If that makes sense to you, go for it. I like to kind of do this, and I'll put this on the board as a flow chart, but I wanted to provide this in a slide. So really, after you draw your Lewis structure and you identify your shape, you can ask yourself a series of questions. So we can look at, are there lone pairs of electrons on the central atom, right? The answer is either yes or no. So yes, there are. Okay, is the shape linear or square planar? Yes, it is. Are the atoms that are connected to the central atom the same? And what I'm saying here is not, are the atoms the same as the central atom, but are the atoms that are connected to the central atom the same? Like in CH4, right? They're all H's. Or in H2O, they're all H's. So if they are the same, yes, the molecule is nonpolar because we would end up canceling out our dipole moments. If they're not the same, then you're going to have a resultant dipole moment, i.e. then the molecule is polar. So XeF4 is square planar. XeF2Cl2 is square planar as well, but we would notice that there is a difference in the dipole moment between the Xe and the F versus the Xe and the Cl. So we go through this again. Are there lone pairs of electrons on the central atom? Yes. Is the shape linear, square planar? No. So that's what we're different from step one. Is there a polar bond? Yes. So in this one, we're looking at any other shape that has lone pairs of electrons on the central atom. Bent, trigonal pyramidal, seesaw, T-shaped, square pyramidal, etc. If there is a polar bond, then the molecule is polar. Like in water, water has a bent molecular shape. If there is not a polar bond, then the molecule is nonpolar, like in hydrosulfuric acid. So they both have the same shape. One has a polar bond, the other does not. And then lastly, right, we're asking ourselves the same question again. Are there lone pairs of electrons on the central atom? No, because we addressed the yes part. Are all the atoms connected to the central atom the same? Yes, then the molecule is nonpolar because now we have all atoms. They can pull in equal and opposite directions if they are the same, right? The example is methane, CH4, so it's nonpolar. If they are not all the same, then you are going to end up with somebody winning the tug of war, example being CH3Cl, where the Cl would have electrons focused towards it.